To determine if a wire or cable is still in good condition, our rule of thumb is to inspect the insulation for any signs of damage such as cracking, cuts, or discoloration. If any of these signs are present, the cable should be replaced immediately. Additionally, if the cable shows signs of excessive heat or burns, it should also be replaced. Cables that are exposed to moisture or chemicals should be inspected regularly for signs of deterioration. The minimum acceptable insulation resistance reading for a cable varies depending on the application and voltage of the cable. For low voltage cables, which are cables operating below 1000 volts, the minimum resistance is 1 megohm per 1000 feet of cable. For medium voltage cables operating between 1000 volts and 35 kilovolts, the minimum resistance is 10 megohms per 1000 feet of cable. For high voltage cables, which operate above 35 kilovolts, the minimum resistance is 100 megohms per 1000 feet of cable. These values are guidelines and may vary based on industry standards and specific application requirements. It is always best to consult with a qualified electrician or the cable manufacturer for specific recommendations tailored to the particular application. To measure insulation resistance, an insulation tester, also known as a megohmmeter, is used. This device applies a direct current, or DC, voltage to the cable and measures the resistance between the conductor and the ground or between two conductors. Cables that fail to meet the minimum insulation resistance requirement should not be used. Even if the cable appears to be in good condition, low insulation resistance can indicate underlying damage or potential for future failure. It is recommended to replace any cable that does not meet the recommended resistance levels. When assessing cable condition, firstly visually inspect the cable along its entire length. Look for any physical damage to the insulation, such as cuts, abrasions, or punctures. Any compromise to the insulation can create a path for current leakage, increasing the risk of electric shock or fire. Secondly, check for discoloration or swelling of the insulation. These signs may indicate that the cable has been exposed to excessive heat, chemicals, or moisture, which can degrade the insulation material and reduce its effectiveness. Thirdly, pay close attention to any areas where the cable is bent or flexed. Repeated bending can cause the insulation to weaken and crack over time, especially in cables that are frequently moved or subjected to vibration. Fourthly, examine the cable terminations, which are the points where the cable connects to equipment or other cables. Ensure that the connections are tight and free from corrosion. Loose or corroded connections can create resistance, leading to overheating and potential failure. Fifthly, if the cable is exposed to direct sunlight, check for signs of UV degradation. Sunlight can cause the insulation to become brittle and crack, reducing its ability to protect the conductors. Sixthly, if the cable is buried underground, be aware that soil conditions and moisture can accelerate the deterioration process. Cables buried in damp or corrosive soil should be inspected more frequently. Seventhly, if the cable is used in a hazardous environment, such as a chemical plant or an area with explosive materials, ensure that it is properly rated for that environment. Use only cables that are specifically designed to withstand the conditions present in the hazardous area. The insulation resistance test performed with a megohmmeter is a critical diagnostic tool for evaluating the integrity of cable insulation. This test applies a high DC voltage to the cable and measures the resulting current leakage. The higher the resistance, the lower the current leakage and the better the condition of the insulation. Firstly, before performing an insulation resistance test, ensure that the cable is de-energized and isolated from all power sources. This step is essential for safety and to prevent damage to the megohmmeter. Secondly, clean the cable terminations to remove any dirt, grease, or other contaminants that could affect the accuracy of the test. Use a clean, dry cloth or solvent specifically designed for electrical cleaning. Thirdly, connect the megohmmeter leads to the cable conductors and ground. Follow the manufacturer's instructions for the specific megohmmeter model being used. Fourthly, select the appropriate test voltage in the megohmmeter. The test voltage should be based on the voltage rating of the cable. For low voltage cables, a test voltage of 500 volts DC is typically used. For medium and high voltage cables, high test voltages may be required. Fifthly, apply the test voltage for a specified period, typically 1 minute. Monitor the resistance reading on the megohmmeter. The resistance should stabilize after a short period. Sixthly, record the insulation resistance reading. Compare the reading to the minimum acceptable values for the cable type and voltage. If the reading is below the minimum, the cable should be replaced. Seventhly, after completing the test, discharge the cable to remove any residual charge. This step is important for safety and to prevent electric shock. For low voltage cables with a minimum resistance of 1 megohm per 1000 feet, consider the following example. If you are testing a 500-foot low voltage cable, the minimum acceptable insulation resistance would be 0.5 megohms, calculated as 1 megohm per 1000 feet multiplied by 500 feet divided by 1000. If the measured resistance is below 0.5 megohms, the cable should be considered suspect and potentially in need of replacement. For medium voltage cables, which have a minimum resistance of 10 megohms per 1000 feet, an example would be testing a 2000-foot medium voltage cable. The minimum acceptable insulation resistance would be 20 megohms, calculated as 10 megohms per 1000 feet multiplied by 2000 feet divided by 1000. If the measured resistance is below 20 megohms, the cable should be carefully evaluated or replaced. For high voltage cables with a minimum resistance of 100 megohms per 1000 feet, consider testing a 100-foot high voltage cable. The minimum acceptable insulation resistance would be 10 megohms, calculated as 100 megohms per 1000 feet multiplied by 100 feet divided by 1000. If the measured resistance is below 10 megohms, the cable should be considered compromised. Remember that these are just examples, and the actual minimum acceptable insulation resistance will depend on the specific cable and its application. Always consult with a qualified electrician or the cable manufacturer for specific recommendations. Furthermore, factors such as temperature and humidity can affect insulation resistance readings. High temperatures generally lead to lower resistance readings, while higher humidity can increase surface leakage, also resulting in lower readings. Therefore, it is important to record the temperature and humidity at the time of the test and to compare readings taken under similar conditions. Trend analysis is a valuable tool for assessing the long-term condition of cables. By periodically measuring insulation resistance and comparing the readings over time, you can identify any gradual degradation of the insulation. A sudden drop in insulation resistance is a clear indication of a problem, while slow, steady decline may suggest that the cable is nearing the end of its service life. In addition to insulation resistance testing, other tests can be performed to evaluate the condition of cables. These tests include dielectric absorption testing, polarization index testing, and time domain reflectometry, or TDR. Dielectric absorption testing measures the rate at which the insulation absorbs electrical energy. A high absorption rate can indicate the presence of moisture or contaminants in the insulation. Polarization index testing compares the insulation resistance reading taken after 10 minutes to the reading taken after 1 minute. A low polarization index can indicate that the insulation is aged or damaged. Time domain reflectometry sends a pulse of energy down the cable and measures the reflections. The reflections can reveal the location and nature of any faults or discontinuities in the cable. Proper cable management practices can significantly extend the life of cables and reduce the risk of failure. These practices include using cable trays and supports to prevent cables from being stressed or damaged, avoiding sharp bends or kinks in the cable, protecting cables from exposure to chemicals and moisture, and ensuring that cables are properly labeled and identified. Regular inspections and testing are essential for maintaining the reliability and safety of electrical systems. By following a systematic approach to cable condition assessment and insulation resistance testing, you can identify potential problems early and take corrective action before they lead to costly downtime or hazardous conditions. Always prioritize safety when working with electrical cables. Wear appropriate personal protective equipment, such as gloves and safety glasses, and follow all applicable safety procedures. If you are not comfortable working with electrical equipment, consult with a qualified electrician. The National Electrical Code, or NEC, provides comprehensive guidelines for the safe installation and maintenance of electrical systems. The NEC covers a wide range of topics, including cable types, ampacity, overcurrent protection, and grounding. Familiarize yourself with the NEC requirements that apply to your specific application. It is updated every 3 years, and staying current with the latest edition is crucial for ensuring electrical safety. In addition to the NEC, other industry standards and best practices provide valuable guidance on cable management and maintenance. These standards may be developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the National Fire Protection Association, or NFPA, and the International Electrotechnical Commission, or IEC. Consider the environmental conditions in which the cable is installed. Extreme temperatures, humidity, and exposure to chemicals can accelerate cable degradation. Select cables that are specifically designed to withstand these conditions. For example, cables used in high-temperature environments should have insulation that is rated for the maximum operating temperature. Cables used in wet locations should be listed for wet locations and have moisture-resistant insulation. Cables used in chemical plants should be resistant to the specific chemicals present in the environment. Be aware of the potential for rodent damage to cables. Rodents can gnaw on cable insulation, creating a path for current leakage and increasing the risk of fire. Protect cables from rodent damage by using conduit or other protective measures. Regularly inspect cables for signs of rodent damage and take steps to control rodent populations in the area. Ensure that cables are properly grounded. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electric shock. The grounding system should be properly installed and maintained in accordance with the NEC requirements. Test the grounding system periodically to ensure that it is functioning correctly. When installing new cables, follow the manufacturer's instructions carefully. Use the correct tools and techniques to avoid damaging the cable insulation. Do not exceed the cable's ampacity rating, which is the maximum current that the cable can safely carry. Overloading a cable can cause it to overheat and fail. Label all cables clearly and accurately. Labeling helps to identify cables quickly and easily, which is especially important during maintenance and troubleshooting. Use durable labels that will withstand the environmental conditions in which the cable is installed. Keep accurate records of all cable installations, inspections, and tests. These records can be valuable for tracking the condition of cables over time and identifying potential problems. The records should include the cable type, size, voltage rating, date of installation, and the results of any inspections or tests. Train personnel on proper cable handling and maintenance procedures. Training helps to ensure that cables are installed and maintained correctly, reducing the risk of damage and failure. The training should cover topics such as cable identification, inspection techniques, insulation resistance testing, and grounding. In summary, assessing cable condition involves a combination of visual inspections, insulation resistance testing, and other diagnostic techniques. Regular inspections, combined with periodic testing, can help to identify potential problems early and prevent costly downtime or hazardous conditions. The rule of thumb for cable condition is to inspect the insulation for any signs of damage, such as cracking, cuts, or discoloration. The minimum acceptable insulation resistance reading depends on the cable's voltage rating, with higher voltage cables requiring higher resistance values. The use of a megohmmeter is essential for accurate insulation resistance measurements. Remember that these are general guidelines, and specific recommendations may vary depending on the application and industry standards. Always consult with a qualified electrician or the cable manufacturer for specific recommendations tailored to your application. Continuous learning and staying updated with industry best practices are crucial for ensuring the safe and reliable operation of electrical systems.